Thank you, Sarah, for that introduction. So yes, indeed, we are going to go through all the scales of geoscience data today and see how EarthNet allows you to articulate every bit of your workflow and make it much smoother than in any other geoscience application that we know of. Here's a quick agenda about what we're going to discuss today. And first of all, we're going to see the problem at hand and where is it possible to add value to the geoscience workflow. We're going to analyze and to go quickly about the legacy workflow and discuss a little bit more the EarthNet workflow and see how EarthNet is built for and by integration. We're going to see the different modules of EarthNet afterwards really quickly, but we'll start with EarthView and with the saying that I've heard many, many times on my geoscience path, that is data knowledge is key to a successful project. If you know your data, you're going to do a much better job. Next up, we're going to look at EarthAI, and EarthAI being EarthNet's workhorse. This is where we deploy the powers of artificial intelligence and put it at disposal of the geoscientist's hands. Finally, with EarthNet, we're going to close up the exploration value chain with EarthInsight, which is our decision-making tool. And then we'll have a question and answers session. So if you have any remaining questions, it will be my pleasure to answer them. And Sarah will have a few closing remarks after that. Problem at hand. There's a few publications that have been put out in the last years that disclose a very tough number to take. Geoscientists spend 75% of their time looking for data. This is not valuable time. This is not anything that anyone is pleased with, but this is something that is a reality. There's a paper published by Geoscience Canada that is about that. There's a few other papers that we've looked into, and all of these say 70 to 80% is non-productive time because of looking for data. It doesn't mean that data managers are doing a bad job, far from that, and hats off to them. But the reality is that incorporating data, building projects and alike is taking a lot of time. And this summarizes in these two workflows. The one on the left I've put up with all my honesty gathered from 12 plus years in the oil and gas industry, really on the operator side. We've got many databases to deal with. These are my yellow boxes, and geoscientists and data managers need to pull data off from these databases, sometimes build local databases for the standalone applications that geoscientists have to work with. There's one for petrophysics, there's one often for seismic well-tie, there's one for interpretation of seismic data, there's one for seismic inversion, and every geoscientist along the way works in their specialist tool. There is little integration. There is a lot of arrows on there. I promise I didn't forget anyone and I didn't add anyone to that workflow, but it's a reality that there's a lot of data exchange. There is a lot of pushing data up and pulling data down from the data repositories. And if anyone omits or forgets or decides to not publish any product back from their work, it creates a big bottleneck in information exchange. Everything crystallizes in the legacy workflow in a standalone decision-making software. It may be integrated, but it really works as a standalone software where it's a combination of all the individuals' work, and this is where everything is reviewed in a peer review meeting. On the other side, we've got the EarthNet workflow, and this has been built from the ground up as a data-centered platform, single platform, where all users can collaborate. And it looks nicer, in my opinion. This is the one I prefer. EarthBank is at the center of that ecosystem. EarthBank is the database that is available to all users, to all modules of EarthNet, of all modules of the platform. And this database is constantly updated with data that is created in every single one of these modules. And everything from EarthBank is accessed by all the modules and all the users using all the modules. We're going to see the three main modules of EarthNet for the geoscience workflow today, which are EarthView, EarthAI, and EarthInsight. And through these three modules, we're going to see all the scales of the data that are available, and that's a data integration really, but we are also going to demonstrate how expertise is integrated by a seamless workflow from one module to another. EarthView, first of all, this is information. And there's always that saying that is information versus data. Data is really the raw stuff. This is where you look at your log data. Information is where you combine that information, or that's where you combine that data in order to gain knowledge about what you have, about the data you have, and you get a better idea of how to solve the problem that you are attacking. Three pictures here show a little bit the different ways to get information from the data that we have. First of all, by integrating all the data, for example, on the map plots. This is all the exploration wells of the Norwegian continental shelf, and you see that we've got a bar for each and every one of these exploration wells with core porosity data. And it's color-coded with the value of the core porosity halfway of the well. This is kind of, you won't see that display everywhere. This is an integration of many wells, several hundreds of wells with core data, and it gives you a better idea of what type of porosity you are able to expect from looking at the cores. Obviously, the log data is the second scale that we can look at, and EarthView allows you to display well logs in your in the regular fashion and the way you are used to looking at log data. In here, we are looking at a density and a gamma ray log for 3 different wells, once again from the Norwegian continental shelf. One third data review engine that we have is the confusion matrix, and the confusion matrix allows you to display cross-plots for several variables. So it's a 1-to-1 cross-plot, but it allows you to find correlations. It allows you to understand which log is influential on the other one. And why is that information rather than data? This is where you prepare yourself to build an algorithm that will be able to detect and to predict some, for example, deep resistivity. You're going to look for correlations and say, okay, it seems that my resistivity versus density has 2 trends, so it means that density definitely plays a role in estimating my resistivity. This is where you prepare yourself for the machine learning algorithms that we're going to discuss a little bit later, where you prepare your feature set and your where you prepare your feature set to estimate your labels, to coin a few data science words. Now, EarthAI, and the first part of EarthAI is for the well data, and it's all the well data and really all of it. First of all, on that first display, you see the cores next to a log, and this is where you're going to be able to apply your core shift, for example, but this is also where you're going to be able to interpret your cores by defining some lithology labels. You will be able to display, for example, here a density log and several other logs as well, and correlate what you see on the core to several behaviors of your cores. In here, we have an increase in a sharp increase in density here when we have this darker material, and by using a few other logs as well, you're going to be able to define your lithology from your core and using your labels. This will be a very interpretive workflow, but the fact that it is integrated in a single tool and not using core photographs that will be interpreted in an Excel spreadsheet is already a major breakthrough, in my opinion. I mentioned all of the well data, and really all of it, and this is illustrated by that second picture here. We have a GeoSonic log in here, and the black curve that is a bit difficult to see, but it's very much behind the green one, is the measured log. And what you can see from the, well, right off the bat is that we don't have any measured TTS for either of these wells here. We have two wells side by side. These ones are from the North Sea offshore Norway. No data was measured for that first well above, well, let's say 2100 meters. And for on the right hand side, no GeoSonic data was measured above that, yeah, let's say 3300 meters. What we're able to do with EarthAI wells is to estimate the missing data. How are we going to do that? Once again, that will be the machine learning part of EarthNET. We're going to look at, well, an algorithm is going to look at the behavior of GeoSonic logs in presence of other logs. So it may be density, it may be deep resistivity, it may be gamma ray, it may be neutron porosity, for example. And we're going to combine these 4 different logs called features in order to estimate the GeoSonic log where it doesn't exist. So first of all, we're teaching the behavior of that feature set against the GeoSonic where it exists. And we use that linear relationship that is built on data that has been measured in order to estimate the log where it has not been measured. All the data means that we are going to create a complete log set that we'll use in the next steps of the exploration workflow. No more data gaps in the logs. EarthAI seismic. We go one scale, well, we go up one level on the scale ladder. I will focus on adding value here. On that first display, you see quite a number of faults. These polygonal faults come from dewatering in the Cretaceous. We're on the Norwegian North Sea here. But these faults are not prospective. They do play a role still because they are important to the seal integrity of the prospect that lie directly below. If the charge comes too early and when if these faults are formed a bit simultaneously with the charge of the prospect below, we may have a risk of leakage. So it's important to define them and to define them as best we can. But I don't know many geoscientists who will spend an awful lot of time defining every single one of these faults here. Adding value is focusing on what is critical for the prospects, but also not doing so much of the boring stuff. Okay, we need to carry water, we need to go chop wood, but after a while, it's very good to know that that interpretation here was not using one single mouse click from me. It was a pre-trained model that we had that understood that these features in the seismic, these behaviors in the seismic corresponded to polygonal faults. I just applied a pre-trained model that we had, and it results in identifying these faults everywhere. And there are many more faults than I would have been able to interpret. Mind you, this is on one slice only, but when you multiply that with 1,000 slices in your seismic cubes, the time value becomes quite interesting. On the other hand, on that right-hand side, we have a problem that is much more difficult to tackle for any geoscientist. We are offshore New Zealand in the Parihaka famous survey, and the prospects are these gullies. And these gullies, they are notoriously difficult to interpret because no auto tracking algorithm will ever be able to pick the right events for the base of these gullies because they are shifting from trough to peak and from soft event to hard event all the time, and the auto trackers struggle with that. That's notorious. What we do here with EarthNet is that we're not looking at a surface or a set of surfaces for the upper boundary and the lower boundary of the gullies. We also look at the insight, and we look at the content of these gullies. Looking at those as an image rather than two surfaces, looking at those as a full body, let's say, allows the machine learning algorithms to understand a little bit what defines these gullies. We don't really need to understand them ourselves, but what we need is to label a few of them and make sure that we label them as best we can. So when I say labeling, is interpreting it manually. And once that labeling work is done, then we can launch the calculation, and this returns a very nice set of gullies that is pretty well defined everywhere. I just want to draw your attention on the fact that we worked on that upper set of gullies. If your eyes are sharp in the early hours of the morning, you will notice that we have a second set of gullies just below. This was not focused on in that interpretation workflow just here. It is possible to focus on really what you want to look at, and that second set of gullies would be another exercise for later on. Building on someone else's knowledge is really key to adding value. So pre-trained models here and collaboration on defining the best possible gullies and not spending too much time, not too much manual work on something that can be automated. Expertise is always needed, but it's not necessary to spend too much time when a lot of it can be automated. EarthAI is data-centered. And when it is data-centered, it means that we are able to analyze the processes, we're able to QC the quality of all the computations. So for each and every model that we create, the models themselves are stored in EarthBank. So it is possible to retrieve all the work that has been done and analyze even after the fact the metrics of the different models that we have run. So that these metrics, they come from a fault model that has been trained on fault data from Australian data, and it doesn't really matter where it comes from, but it is real data and allowing you to see the progression of the model quality. So analyzing the cost function and analyzing whether you are actually building a good data-wise model is really the key to gauge the quality of your work. It can be dangerous when you have complete black boxes to just click on a button and just ingest the results as they come. In EarthNET, we have decided to put the data at the center of everything. So not only are you able to customize every single parameter and hyperparameter of your machine learning model, but you also are able to review everything. So you know that the model that you prefer, the one that would give you the best visual impression, is also the one that has the best metrics. This is an example of that. And on the other hand, this display here comes from the model analysis of a 3D property prediction exercise. And we first of all see the correlation for predicted data versus measured data. So in here, we are estimating an acoustic impedance cube from a set of wells that is about 10 wells here. And we see that we train properly. So it means that the model is able to create a valid linear relationship that estimates acoustic impedance from the other features that we have chosen. And this is the check that that relationship is valid also for parts of the wells or for new wells that have not been trained on. So this is a very good quality check. Geoscience is always in the center of everything we do. So alongside these cross plots, you will see some well plots that allow you to check that your predictions do make sense in terms of log data and more. The thing is, you can always, and you should always have a geological sense check by looking at either your seismic data and see where your faults are located, where your gullies are located, to see whether that acoustic impedance volume does make sense to you. The geoscientist is the expert, and the expert always will have the final words, because otherwise robots would be exploration managers, and we're not there yet, and no one wants that to happen. Speaking of decision making, here's a slide of EarthInsight, and EarthInsight is really where geoscience data become prospects. On that slide, you see a snapshot from the Barents Sea, so in the north of Norway, and you see several bars on top of several wells. These bars they correspond to the mean porosity of the reservoir in here, and the height of the bar is the thickness, the net thickness of the reservoir, where the color corresponds to the mean porosity of the reservoir itself. I filtered on the Cobber Formation, which is an important reservoir in the western part of the Barents Sea, and in here we're basically in the central Barents Sea here. But we can see that we are able to combine some pretty advanced calculations, net to gross, net reservoir thickness, reservoir mean porosity. These are the types of parameters, reservoir parameters, that are discussed at peer review meetings. It is very interesting to have this in the same application as the rest of your technical workflow, because if anything changes, if you decide to change anything, everything is at your fingertips. If you decide to change one model to apply your porosity and your water saturation, this is where the computation comes from. You can see also that you have your cutoffs defined here. No black box there, but if you should work with another set of porosity estimations, you can do that. Another set of water saturation estimations, you can choose that here. And this is the guarantee to make your peer review meetings go much, much, much faster. First of all, because all your data is there, all your data is available, but also because that data has been seen and used by all the geoscientists all the way from the core interpretation through the well log editing into the well log curve fill, and also all the way into seismic interpretation and property volume computation. EarthInsight is where everything really takes the shape of a prospect. Another tool that we're proud to have in here is a centralized summary of the work being done in the project. Like I said, in EarthNET, we have a single project for all users, and that project is used as a single source of truth for all data. EarthBank is the guarantee of that. And as such, we have a comprehensive registry for quality assessment of all the operations done on the project. You can see that done by every user. If you want to, you can review all the work, and that allows you to get back, for example, during the peer review meeting, and really check if you're in doubt about what's that labels for faults, what they really are made of. And you can always review everything, and being able to track down all the operations done on a project is the best quality assessment step you can make. Integration of data and integration of disciplines. These two ideas have been the core of EarthNET from the ground up. We've seen the influence of EarthBank quite a lot during that presentation here, during this presentation, with EarthBank being able to distribute data to every single module of EarthNET and being able to distribute that data to every single one of the users of that project. EarthView is all about viewing the data and understanding what they are made of. We've seen these screenshots just before. EarthAI is making use of the data we have, both wells but also seismic, and creating and generating volumes of interest, maybe volumes of faults, it may be volumes of properties like the acoustic impedance cube that we have here. We display it in 3D here. EarthAI brings you from 1D to 3D. EarthAI also allows you to perform seismic EARTHAI. EarthAI also allows you to perform time to depth conversion. by generating quality controlled velocity volumes starting from the logs. And this means that all the disciplines are integrated and results in a smooth peer review meeting using EarthInsight in here. Everything is updatable, everything can be reviewed, updated, and changed on the fly because everything is available in EarthBank and everything can be made available to every single one of the modules that are in use. This concludes my talk, and